regarding YouTube. I think we should be live now. Sorry for that. Thanks for the question. Graph neural networks, they process information on graphs, for example, on the nodes, in a graph neural network, you can have information about a node A and a node B that are adjacent to each other. This information is combined into a message, which is then aggregated to the incoming nodes. And graph neural networks also have a very important symmetry property, namely that if you permute the nodes, then apply the network, that yields the same result as applying the network and then permuting the nodes. And we can go on and on. Another example could be processing information on groups or homogeneous spaces, such as spheres. So we may design neural networks that operate on signals on spheres. And spheres can be rotated and their signals along with it. And we may want to have that applying the neural network and then rotating the signal yields the same result as rotating the signal and then applying the neural network. So these are all instances in which we have data living in some on some geometric space, and we want to apply neural networks to process these data. But the spaces have symmetries, and we want our neural networks to respect these symmetries. And I'll go into more detail about what all these words mean. So kind of the story that I want to tell today is how the basic tools from category theory, in particular natural transformations between functors, allow us to generalize a whole swath of concepts from geometric deep learning into more general things, and like to explore a couple of applications where we can see how we can build different or more expressive neural networks or get more elegant viewpoints on neural networks that already exist. And the story of the generalization is roughly as follows. So we may have a group, for example, a translation group, where we can translate up or down by a couple of pixels. And these groups can be represented. This means that we have a space of signals, for example, images, and we have a rule that says how these signals transform if we translate them. And then one can try to build neural networks that are equivariant with respect to those, meaning that if you have a if you have an image and we have a neural network that processes this image, for example, turning it black and white, and then translating it, this should yield the same result as first translating it and then applying the neural network. And this is called equivariance. The story of generalization is basically very simple. We're gonna see that a group is just a special instance of a category. Also, this has been previously mentioned by Petter. We will see that a representation is a special case of a functor. And we'll see that an equivariant map is a special case of a natural transformation. And I'll try to give you a lot of examples of natural transformations. And so they become intuitive and show you what kind of neural networks and similar things you can construct with them. So let's go to the basics. Let's define our concepts. So just to recap, category, you've seen this by now, but I'm gonna, just for completeness, repeat it for you. So a category consists of a universe, like a set or something larger, of objects, and a collection of morphisms between them, satisfying certain axioms, namely that for every pair of objects where the first one maps to the same type, to the same object as the second maps from, there's a composition rule that combines them. For every object, there is a identity morphism to itself, and this identity morphism needs to satisfy a identity law, meaning that if you apply the identity before or after the morphism, you get the same morphism, and composition needs to be associative. we'll be referring to the set of morphisms from object A to an object B as the hom set from A to B. In any category, we can identify a certain class of special morphisms called isomorphisms. Isomorphisms are morphisms from A to B, such that there is a morphism from B to A, that if you pre or post compose the first morphism with the second, you get the identity. And this is just a generalization of an invertible map from sets to general categories, which are called isomorphisms. And groupoids are a class of categories in which all morphisms are isomorphisms. And these are of crucial importance for geometric deep learning, because basically they describe symmetries. They describe when certain objects are essentially the same and thus should be processed by our neural networks in equivalent ways. A special class of an isomorphism is an automorphism, and that is an isomorphism of an object to itself. An example of an automorphism is we can have a sphere and we can rotate it to itself. That is an isomorphism to itself. That's an automorphism. And automorphisms play an important role because they're going to give constraints that neural networks need to satisfy when we make them respect the symmetry structure of our problem. Geometric deep learning, as it's commonly told, is all centered around groups, and we're going to later generalize that to groupoids and categories. A group, as you've seen before, is a set with a binary operation, and this operation needs to satisfy an identity law, an associativity law, and an invertibility law. And as we know by now, a group is simply a groupoid with a unique object. So in a way, we can see this generalization story from groups to groupoids as just thinking about groups, but then with additional objects. Note that any groupoid also has groups inside of it, because for any groupoid and any object in the groupoid, the set of automorphisms form a group, which if you like to play around with, you can try to prove that yourself. It's pretty straightforward. Functors are maps between categories. So if we have a category C and D, then a functor from C to D does two things. It maps objects in C to objects in D. And I see a question. What's the difference between a group G and a group BG? That's a great question. It's basically, how I see it is basically a notational thing. The group G refers to a group in the common notation of a group, and what I call BG is a category with a single object whose set of morphisms is the set of groups. Sorry, there's a question by Andrew.
Oh, yeah, I just wanted to sort of add to that. Like, some people will use G to mean the category whose objects are elements of G, and that's a monoidal category, and this is a different thing. So that's why it's quite common in the literature to see BG to distinguish these two things.
Makes sense. So functors map objects in C to objects in D and morphisms in C to morphisms in D. And crucially, this must respect the structure of the group. What does that mean? Of the category. What does it mean? It means that for any object, the identity is mapped to the identity, and that composition in C and then mapping with the functor yields the same morphism in D as applying the functor to the individual morphisms and then doing the composition in the category D. An important case of functors are group representations, and we can see groups themselves as abstract objects with abstract rules, but we in deep learning we often have vector spaces of data, and a group representation encodes how these vector spaces transform when we act with the group. So an n-dimensional group representation is simply a map from the group to n by n matrices, such that composition is preserved, so that the group composition translates to matrix composition. Group representations tell us how groups transform in the space of linear transformations. Sorry if all of this is rehashed from Peter, but I thought it's very important to go over these basics again. And so these group representations can be very elegantly thought as functors, and namely functors from the category, I should have written BG here, of a group to the category of vector spaces. And these category of vector spaces has as object vector spaces and as morphisms linear transformations. So then a functor from the category corresponding to a group to a vector space assigns to the unique object in the group category the vector space, and to each morphism in the group category a linear transformation. And the functor rule that composition is preserved tells us exactly that group multiplication corresponds to the matrix multiplication of the matrices of the group elements. Now we'll come to the new part, equivariance. So equivariance is a map between vector spaces that or other kinds of spaces in which groups can act, in which similar inputs are processed similarly. So to give an example, imagine we have a group, the cyclic group of size n, which contains the integers n, and the group multiplication is addition modulo n. Then we can assign a vector space. Then we can think of a vector space, say the n-dimensional vector space. And I give here an example for the case n is 5, where we have a vector of 5 numbers. This group has a representation. There's a representation of this group on the vector space, and it basically translates signals on the vector space. So for example, we can add by the group element -1, we can add it on the vector space, and we see that the vector is shifted to the left by 1 position. An equivariant map is a map from the vector space now to itself. And this needs to satisfy an equivariance criterion. And this is exactly what I said before. This map is equivariant when, for all group elements, if we first apply the map alpha and then act with the group element, or first apply the group element and then the map alpha, that the output is the same. So this diagram commutes. In this concrete case, we would require that if we apply the map alpha, we get this output, which in this case is just taking the difference between the vector elements, and then rotate it, that we get the same result as first rotating it to the left and then applying the group element. There's a question, shouldn't Cn have elements 0 to n-1, otherwise no identity under addition? That is a good point. I think we could, I think that would make for a more natural representation. Yeah, thank you very much.
And n is 0.
N is 0. Yeah, you can also do it that way. Yeah, thanks. Now I have a question for the people who have been paying close attention. If we have these kind of features and this kind of group, namely a rotation of the vector, does anybody know what the general class of equivariant maps is? So please, if you have an idea, please feel free to write it in the chat or the Q&A. I see.
Could you maybe restate the question just one more time?
Yes, of course. Thank you, Bruno. The question is, we have a group G, the group G of addition modulo n, and we have a vector space, the n-dimensional vector space, and we pick the representation of G on this vector space that rotates the vector. And so we have a translation modulo n. The question is, what's the general class of equivariant maps between these two representations? Periodic functions. Interesting. The answer I was looking for is convolution, as is used very widely in deep learning. So convolution is the following. So if we have an element of this vector field, so an n-dimensional, isn't this a ring? Yeah, it's very related. Yeah, it's you can see this as a ring also, the group ring in particular. So a filter is an element of the vector field, and we can transform a vector field by convolution, which basically does the following. So we have an input field and a filter, and we want to know the vector component at the ith vector component. The output of that is we sum over the vector field and multiply by our filter, where we shift the filter by according to this formula, and this is basically the foundation of all of neural networks. So this defines a convolution in 1D, and you can show with a simple proof that I'm not going to go into now, but you can maybe look into in the slides if you're interested. You can see that this is equivariant relative to translations. And thus all the convolutional neural networks that are used in practice, at least the simple ones, are translation equivariant. There is some interesting work that generalizes these kind of convolutions to compact groups acting on homogeneous spaces like spheres. And there's even a completeness result saying that all linear equivariant maps are convolutions of this type. So to give you some examples, equivariant CNNs, they work as follows. So imagine we have a spherical input here, and a normal non-equivariant CNN would map a signal like this to another signal. And this is a random untrained CNN, so it doesn't do anything concretely. If you then rotate the input, you see that the output transforms, which if you rotate it back, does basically arbitrary things. An equivariant CNN, on the other hand, takes the input, produces an output, and if you rotate the input and then rotate the output in the opposite direction, it stays the same, meaning that such a network does satisfy that applying a rotation, then the network yields the same as first applying a network and first rotating the input and then applying the network. An important caveat I should say here. So here we're now talking about a rotation equivariance. So normal CNNs are translation equivariant, but not rotation equivariant. If you do it carefully, you can design CNNs that are equivariant not only to translations, but also rotations, and then you get output like these. This kind of equivariant preserves information. So I don't quite follow the first question from Situ. This kind of equivariance preserves information. I'm not quite sure what the question means. The second question is, Lucino says that he doesn't think, or they don't think, that standard convolutions are truly equivariant, and this is true. There are border effects in normal CNNs, but if you define everything periodic, then they are a translation equivariant. But that's often not done in practice for practical reasons, making the equivariance only approximately true. There's a very interesting question by Alisa. How does augmenting the data compared to baking equivariance into the architecture? That's a great question. So you can imagine that in a way these try to achieve similar goals. So the one approach you can do to achieve this rotation equivariance is by constraining your class of functions such that for any parameterization this equivariance property holds. An alternative strategy would be to augment your data set by transforming the inputs, all the inputs and outputs you provide to the network, and then train on that. There are, I think, two good reasons for why the explicit equivariance can be preferable. The first one is that if you build a network in which all your layers are equivariant, then you have a stronger constraint than only requiring the inputs and outputs of your whole network to be equivariant. So in a way, it's more akin to augmenting not only the inputs and outputs, but also every intermediate layer. So this creates a very large augmentation space then. A second reason why built-in equivariance may be preferable is that it's about generalization. If you do augmentation, then you only augment your training data set, and you have no guarantees of equivariance for your test set. If you hard code equivariance, then you do have the guarantee that also in your test set, your network is equivariant. A question by Matthew. For given group and representation, then any A which is equivariant over P is a convolution. So for any, this holds for linear maps. Yeah, so any linear A that is equivariant is indeed a convolution. And this holds for translations, and this paper I mentioned by Condor and Trivedi show that this holds more generally for groups and homogeneous spaces. Do equivariant, next question, do equivariant CNNs outperform traditional CNNs? And in metrics versus. So this is, so I guess the question is, in practice, is it always better to use equivariant CNN? First of all, if your problem is equivariant, or it does have a symmetry, only then it can make sense to use equivariance. For example, if you do ImageNet, you don't actually see rotations of every object equally frequently. So the problem doesn't actually have a rotational symmetry. So then definitely you don't always want to use equivariance. There is, it's a complicated question. It can be preferable. It's not guaranteed to be preferable. I can cite some survey work in Zulip that tries to study the question when, in the context of CNNs, it is preferable to use equivariance. Is there an equivariant CNN that is equivariant to mirroring? Yes. If you look in Cohen Embedding 2016, then you see an instance of that. And I think I'm gonna maybe I'll leave the next questions for later. If it's okay with you, I'm gonna continue. Another example of equivariant networks are spherical CNNs. So this is very similar, but we may have a signal on a sphere and a neural network that takes its input and outputs a new signal on the sphere, and then we can make this equivariant so that if you apply the network, then rotate the sphere, you get the same output as rotating the sphere, then applying the network. So these are just some examples, and I'll add the citation that's missing here when I upload the slides. And these are just some examples of how equivariance plays a very important role in geometric deep learning. So now let's come to the concept that we're all here for, namely natural transformations. The natural transformations are going to be the generalization of equivariance, but this holds now for any two categories and any two functors. So given two categories C and D and two functors from C to D, a natural transformation from the functor F to the functor G consists of, for each object in the category C, a morphism from F of A to G of A, and we call this the component of the natural transformation for object A. And this requires a commutation relationship for every morphism in the category C, morphism F in the category C. So note that we can map the morphism F to a morphism in D by applying the functor F. And we can also map the morphism little f to the category D by applying the functor G. And now we require that if we apply the component A and then the morphism F seen through the functor G, that this yields the same output as first applying the functor, the morphism F through the functor big F, and then the component alpha B. So this is what a natural transformation is, and this is a lot of words. And I hope to make clear to you that this is a very useful concept with many instances. And first of all, I'd like to show to you that equivariance is just an instance of naturality. So we can think of a group G can be seen as a category, BG. Representations of the group, as we've seen, can be thought of as functors from the group category to the category of vector spaces. And then an equivariant map is just the natural transformations between the two functors. And you can see that by just comparing the diagrams. So in that case, we here have a vector space V, here a vector space V prime, here a vector space V, here a vector space V prime. Here we have the group action as seen through the first functor, the first representation. Here we would have the group action as seen through the second representation. There is only one object in a group, so there's only one component alpha, and then we recover that the naturality diagram is exactly the group equivariance diagram we have seen before. So let's now come to a couple of examples of naturality. So a pre-order is an instance of a category in which there is at most one morphism, often written lower than or equal, between two objects. And examples are like the real numbers, where the one morphism exists if the first real number is smaller than the second real number. Now a question for the audience. What is a functor between two pre-orders? So what does it mean for a functor between, so we have two pre-orders P and Q, and that means that they have at most one morphism between between any two objects. And the question is, what are the functors between them? And I get a lot of good answers in the chat. These are order preserving maps. Yes, indeed. So a functor is a monotone map because whenever we have a morphism from P to Q, we need to have a morphism from f of P to f of Q. And because there's only one morphism, the composition rule is automatically satisfied. So any monotone map is a functor between pre-orders. Now let's see the next question. If we have two such functors, what would natural transformations between them be? Another question. If you know it, please put it in the Q&A. inclusions. As you come by. A natural transformation is simply saying that a natural transformation from F to G basically just means that the output of F at P is smaller than the output for G for all P. So basically saying that the monotone map F is element-wise or point-wise smaller than the monotone map G. And you can see that because we require for all objects P a morphism from F of P to G of P. This morphism is just a smaller than relationship. And in this particular case, you would also have the commuting diagram, but this commuting diagram is trivial because there is only one morphism between, at most one morphism between any two objects. So all diagrams are always commute. To give another example, we can make a functor from vector space to vector spaces, and it maps a vector space to the product of a vector space to itself, and it maps a linear map to the linear map applied to the two copies individually. And a natural transformation now would be a linear map from for each object, for each vector space V, from V to the product of V with V, satisfying this commuting diagram. And you can convince yourself that all such maps basically go from V to two copies of V, and then in this case it's allowed to apply an arbitrary scaling to the two copies. So these are all the natural transformations between the functor identity, which just maps a linear map to itself, to the functor that maps it to two copies of itself. If you will, we saw in Bruno's last talk, we heard about supply of comonoids, and you can see that in any Cartesian category, you get such morphisms that map from one copy of the object to two copies of the object, and also a morphism that maps from each object to the unit of the monoidal category. And this gives a supply of comonoids. And you can see, maybe that's an exercise you can do it. You can do and write in Zulip about if you're interested. That these maps are always natural transformations. There's a very interesting example of natural transformations given in the context of functional programming. We can make a functor that maps sets to sets, and it is the list functor. It maps a set A to the set of ordered lists of elements of A. So it's so for example, the set applied to real the list functor applied to the set of real numbers gives you just finite lists of real numbers. Another functor we can make is the constant functor. It maps every set to, in this case, the set of natural numbers, and it maps every morphism to the identity morphism on the natural numbers. And now we can construct a natural transformation which maps from the list functor to this constant functor. And what does it do? Well, one of the natural transformations we can cook up is the length functor. It takes a list and it outputs the length of the list. So this is natural because if we have a list of objects of set in set A, then we apply the functor, which applies the function f element-wise, and then apply our list function. Then we get a natural number, and this is the same as if we applied the list morphism on the original list. And this is a triangle and not a square, because we say that any morphism F is applied to the identity map on the set of natural numbers. And there's a link here by Bartosz Milewski on a blog post saying that all these kind of parametric functions give rise to natural transformations. I find it very interesting. A further example I'd like to give is monoid equivariance. So a monoid is very akin to a group, but then without the existence of isomorphisms. So not every element is invertible, and a monoid is equivalent to a category with only one object. To give an example, we can think of a monoid of non-negative numbers with addition, and it's clear that these don't have inverses. And we can one instance, or actually representation of this monoid will be a functor from this monoid. So B here again means to basically the category with a unique object and whose morphisms correspond to the elements of this monoid, to the vector spaces. And in this case, it would map images to blurrings of this image. And it's clear that blurrings don't have inverses. So this is an example of a monoid action on the space of images. And you can and these blurrings are closely related to scalings of the images, because you can basically think of a blurring as thinking as a representation of the image in a sort of larger scale. And by making natural transformations between such functors, you can build neural networks that are equivariant to scaling. And this is done by Worrell and Welling in a paper called Deep Scale Spaces. And I think it's one of the first examples of equivariance of something else than a group in geometric deep learning. And we can, in this framework, very nicely just think of it as a natural transformation between categories that don't represent groups, but monoids. We can think of natural transformations as maps between functors. And this gives rise to a very interesting structure called a two category that doesn't just have object and morphisms, but also morphisms between morphisms. So first of all, we can define a functor category. So given two categories C and D, a functor category is the category whose objects are the functors from C to D, and whose morphisms are natural transformations between them. And these indeed satisfy the axioms of the category of unitality and associativity. A very interesting example thereof is the category of graphs. So we can construct this category. It just has two objects, two identity morphisms, and two morphisms from the object E to the object V. Notice this is not a commuting diagram, it's just a representation of the diagram, a presentation of the diagram of the category. And now if we think of functors from this category to the category of set, what does it contain? Well, it contains a set G of E, a set G of V of edges and vertices, and it contains two functions from the set of edges to the set of vertices. And this exactly encodes a graph, because a graph has edges and it has vertices. And for each edge, we can map to the source vertex, and we can map to the target vertex. So this corresponds to a directed graph. And what is so interesting about this is that now we can just say what is a natural transformation between two such between two such functors from this category par to the category of set. And this corresponds exactly to a graph morphism, because we map the set of edges to the set of edges of G to the set of edges of G prime, and the set of nodes of G to the set of nodes of G prime. And then we have a commuting diagram. Basically, if we go from this edge to its source vertex, and then apply the component that maps us to the source vertex in the graph G prime, or first map between from the edge in G to the edge in G prime, and then to the source vertex, then the vertex that we end up at must be the same. So this exactly is also what is encoded by a graph morphism. So this shows that if we define a concept that we find interesting as a functor, then the natural transformations between them give a very good notion of what a morphism between these concepts are. And so this motivates us to define a category of graph simply as the functor category from the category par to the category of sets. The question is, what does par stand for? It stands for parallel arrows, because it's got two arrows that are parallel from the same object to the same object. We can also make diagrams of natural transformations. So here we can see. So this is how we draw a natural transformation. So we have two functors, f and g, from category C to category D, and a natural transformation between these functors is written as a double arrow between them. We can also compose natural transformations. So one we already saw, this is the composition in the functor category. So if we have three functors from the same object C to the same object D, and we have a natural transformation alpha from F to G, and a natural transformation beta from G to H, then we can compose them into a natural transformation B after H from F to H. And this is called vertical composition of the natural transformations. Another thing we can do is horizontal composition. So if you have three objects, and alpha maps from functor F to F prime and beta from G to G prime, then we can compose these into a natural transformation from G after F to G prime after F prime. This is called horizontal composition of the natural transformations. And you can also, in this case, if we have a natural transformations from G to G prime, we can think of this here as a identity natural transformation from F to F, and then we can apply horizontal composition to get a natural transformation from C to E, and this is called whiskering. So with all of these composition rules, you can form something that is called a two category, and it generalizes over one category by adding two morphisms between the one morphism. So in this case, and this has to satisfy a lot of coherence axioms, but in this case, these are satisfied. So we get a two category cat whose objects are categories, whose one morphisms are functors, and whose two morphisms are natural transformations. There's a question: are there natural computer science neural network analogs to higher dimensional categories? I don't know. Maybe we can discuss that afterwards or in the student. There was a question in an earlier session of the course asking if we can talk about Gates equivariance. So I thought to include it also in this presentation. Here I talk about a very simple form of Gates equivariance. So we have, in which case we would have d-dimensional data, and we would map linearly from a d-dimensional vector space to a d-dimensional vector space with a matrix. And now importantly is that the basis, or also called gauge, varies per data point. And now we have two different versions. One is that if we don't know the basis in which the data is presented that we're going to process, we can only apply a single matrix to the data, regardless of the basis. And we'll see that this leads to equivariance relative to gauge transformations. But if we do know the basis in which the data is presented, then we can have the map that we apply depend on the basis. So let's look at the first case. So there is a group of invertible D by D matrices, which we'll think now as basis transformations. And this can act on the d-dimensional vector space by basically by itself. So a matrix can act on a vector space by matrix vector multiplication. Now, if we want to be equivariant relative to this group, then the only thing we can do is apply scaling. This is something related to something called Schur's lemma. But so basically it means that whenever we have no clue in which the data is presented and then apply our linear neural network, our linear transformation on the data, then there's very few parameters that we can apply. All we can do is scale the inputs by some real number. To discuss the other category, the other case in which we do know which basis our data is presented, we can define a category of bases. So if we have some vector space without a canonical basis, then we can define a category in which the objects are bases. And the basis for a vector space is a map or an isomorphism, a bijective linear map from the standard basis to this vector space. And the morphisms in this category would be basis transformations. Sorry, changes of the would be bijections from RD to RD, such that this diagram commutes. So we can map from the basis B to the basis B prime with such a change of basis G, and then we require the diagram to commute, meaning that is there a reference online for this construction? I'll have a look at that and let you know. But basically, you can see this as the action groupoid acting on the space of bases. And I'll refer to this maybe in Zulip. So you can see this as, but it is also in slightly different language used a lot in the context of associated vector bundles in basically equivariant neural networks applied to manifolds. And we can have a functor from the category C to the vector space by mapping everything to every basis to space RD and mapping the basis transformation just to the matrix G. So why do I say all this? Well, now we think of what is a natural transformation between these two functors and till. So now we have basically the same diagram as before. So we have the space RD, and we have we can have a change of basis, and we have a natural transformation. But the important difference here now is that the natural transformation has a subscript, namely the natural transformation can differ depending on how the data is presented, depending on the basis in which that we see the data in. And we saw that if the map cannot depend on the basis, then it's very limited. All it can do is multiply by a scalar. However, if the matrix that we apply can differ on the basis that we use, you can make an easy argument to say that we can use basically any matrix at all. So if we have any matrix from between these vectors, these abstract vector spaces V, then we can just express this in a basis, giving it a matrix from RD to RD, and in a different matrix, in a different basis, we just get the matrix expressed in a different basis. But we can freely pick the one matrix, and then naturality says that in each different basis, it must be expressed. It must basically have a basis transformation. So if the so summing up, so if we don't know the basis, then we have an equivariant map. It has a single component, and this is very strongly constrained. And this corresponds to scalar multiplication, or it's so constrained that it must be scalar multiplication. But if we do know the basis in which our data is presented, then we can we can have a natural transformation which can depend on the basis, and this can actually be any matrix which we just express in different bases. If this matrix must be constant in the basis, then we're back to the first case above. So this is just an example of how we can use categories to encode the symmetry properties. There's a question. For a general manifold, there exists such a natural transformation for each tangent space. Yes. So this would, and that's kind of what I sketched here. So if we have a vector field on the sphere, and we here assume that we know what is the top and bottom of the sphere, so we don't have any symmetry constraints. So the symmetry we should be able to allow to express any transformation between signals on the sphere, because we don't have any symmetry constraints. But if we have vector spaces on the sphere, we still need to choose a basis for the tangent planes. And we can, so if we have a vector here, which is denoted by the green vector, we can choose a basis in which the green vector has some coefficients, or a basis in which it has other coefficients. And saying that we have such a natural transformation means that we apply a matrix on these kind of signals, but the matrix can depend on the basis that we have chosen. And this is necessary, for example, in the case of spheres, because there is no canonical way or not a global way of picking a basis for all the tangent planes. So we need to basically steer our basis. We need to pick arbitrarily some basis, express our matrix in the proper basis, and then apply it. And then naturality says that this is basically consistent. So what we've seen before is we have a groupoid, and we're going to build natural transformations to those. We can see that there's actually some shared structure in these kind of whenever we do that. So imagine we have a groupoid G, and we have two functors rho and rho prime that map the groupoid to the category vector spaces, and we have a natural transformation alpha between them. So what we would see is that for all the automorphisms from A to A, which are objects in G, we get a diagram of this shape. So we get for the component A, we map from A, from rho of A to rho prime of A, and then we apply the automorphism, and then we apply the A component of the natural transformation, and the naturality requires that first applying the automorphism and then the component the A component, use the same result as first applying the A component and then the automorphism. So this is exactly an equivariance constraint. So you would get that this component A must be equivariant to the group of automorphisms of the object A. Whenever you have an isomorphism from an object A to an object B, you get this kind of diagram where if we apply the A component and then the isomorphism, we need to get the same result as applying the isomorphism and then the B component. And because all these, because these arrows, the vertical arrows here, are isomorphisms, because this is a groupoid, this means that the B component is fully determined in terms of the A component. So if you want to design such a natural transformation, what you would do is you would look at like the A component, you would constrain it according to the automorphism group of the A component. And then for all the isomorphic objects, we get that the natural transformation is fully constrained. And if we have a object that is not isomorphic to A and B, then we get that the component of the natural transformation is independent from the first two. So in conclusion, we get for all the automorphisms in our groupoid, we get constraints, and for all the isomorphisms, we get weight sharing between the components, because that's what this diagram dictates. Let me skip this slide. Right, so now we'll come to we want to apply what we just developed to graphs. And this is most of the work here, or this is mostly taken from work we did in 2020 in a paper called Natural Graph Networks. So we look at the groupoid of graphs. There are many different ways, isomorphic ways, to encode the same graph. And if we apply a neural network on the graph, then we want these. Then we want the neural network to process these graphs similarly. So we call now the category of graphs graph, and we say that the nodes are labeled by natural numbers. And here we only consider isomorphisms. So we discard all the graph morphisms that are not isomorphisms. And this gives us a groupoid. And the reason we do that is because whenever we see an arbitrary graph in our algorithm, we can, at least in theory, identify which isomorphism class it belongs to. But we cannot, but we can only identify it up to isomorphism. So we want to build this ambiguity of that is given by all the isomorphisms. We want to build that into the network. We generally don't want to also build like a naturality relation with for all the non-isomorphic graph morphisms. I think it's an interesting question. Or actually, there's an answer to the question. If you want to be natural relative to also non-isomorphic graph morphisms, then you get very strong constraints. So what you can do, basically get very trivial neural networks. So you get very constrained natural transformations. There's a question. Are equivalent relations a special type of groupoids? I'm struggling to come up with examples other than groups. So the first question by Federico is, are equivalence relationships a special type of groupoid? Yes, very much. So it's an equivalence relationship. So basically, you say that an equivalence relationship is like a groupoid, whereby any two parallel morphisms are the same, because an equivalence relationship doesn't encode anything other than that objects are equivalent. and your there's Andrew is raising a hand.
Yeah, I just wanted to chime in. As far as examples go, you can get an example by taking any category and just throwing away all of the morphisms that are not invertible. So that's sort of, that should give you a lot of examples to work with.
Yeah, and that's basically also what we're doing here. We previously defined the category of graphs as containing any graph morphism, but now here we're throwing away everything that is not an isomorphism. This is sometimes called the core of a category, and then you're left with only isomorphisms. Hopefully it also answers Yeva's question. What are the morphisms? Well, these are here graph morphisms that are isomorphisms, and this basically means I'll give an example of that in a sec. Then there is a question. So seeing the graph as ambiguous with respect to automorphisms is saying that permuting the vertices of the graph data does not guarantee that we have the same graph. Let me defer that also. So imagine we have this graph. It has 4 nodes, and it has edges as encoded here. And we can also think of this as an adjacency matrix, where we get a 1 when there's an edge present and a 0 otherwise. So this encodes a graph, and this is an object in our category. A graph isomorphism here is a map to another graph, which is a map from a set of nodes to another set of nodes, such that whenever 2 nodes are that if and only if 2 nodes are connected in the first graph, that they must be connected in the image of the node bijection also. So here that would mean that we map sorry, I should say this properly. Yes. Okay. So this is a graph G. This is a graph G prime. The graph G has a set of nodes, and those are the nodes labeled 1, 2, 3, and 4. And the set G prime also has a set of nodes labeled 1, 2, 3, and 4. In addition, the first graph has a set of edges. So you could say that is the set containing 1, 2, 1, 4, 2, 4, and 1, 3. And so does the second graph. A graph isomorphism is a bijection of the set of nodes and a bijection of the set of edges, such that if we map an edge from G to G prime and then go to the source node, that we get the same node that if we would map the edge. So to give an example, we look at this edge from 1 to 3. I didn't make these directed, so let's take 3 to be the source node. So here we map this, we take 1 to be the source node. So here we map this edge to this edge. Sorry, my screen is lagging. So the one horizontal edge to the other horizontal edge. And then we take the source node, which is 2. That this should yield the same result as here we map to the source node, and then we apply the bijection of nodes, which in this case maps nodes 1 to node 2. So that defines a graph isomorphism, and it basically means that nodes and edges are mapped consistently between each other. A special case of a graph isomorphism is a graph automorphism. So here we map the set of edges to the set of edges, and to the same set of edges and then set of nodes to the same set of nodes, such that this consistency requirement holds. So in this case, if we map node 2 to node 4, then we get the exact same set of edges, and we can see that in the adjacency matrix also. If we map node 2 to node 4, the adjacency matrix is transformed by swapping the second and fourth row and column, and we see that if we do that to the matrix, that the matrix is the same. And this makes it an automorphism. It's an isomorphism that if we apply it, where we end up at the same graph. So I hope this answers EF's question. What are the morphisms here? And then there's a question by Lucino. So saying that the graphs are ambiguous with respect to automorphism, saying that permuting the vertices does not guarantee we have the same graph. So in this case, isomorphisms may change the set of graphs, sorry, the set of edges. Automorphisms leave the set of edges the same. Usual graph neural networks are permutation invariant. I would say that usual graph networks are permutation equivariant because the vector features transforms if we apply. So we can permute the vertex features, then apply the network is the same as permuting the vertex features and then applying the network. Adjacency matrix are similar up to permutation matrices. That is correct. Yes, Alberto is making a correct statement. A graph isomorphisms are given by permutation of the adjacency matrix by the same permutation matrix on the left and right of the matrix. Matthew is asking, so it isn't required that the image of a node neighborhood is the neighborhood of the image of a node. That the image of a node neighborhood, so if we take 2, let me think about that. So if we take node 2, here we would map it to 1. I think this is still required. I think a graph isomorphism does satisfy this property. So if we, so the question is it required that if we have a node neighborhood and we map it with the isomorphism, that this is the same as first mapping with the isomorphism and then taking the node neighborhood? So if we take 2 and we map it to 1, then we take the neighborhood, we get 2 and 4. The diagram is confusing because in the original 2 doesn't connect to 3. Yes, yeah, but you should permute an yeah, so we take a node 2, we map it to node 1, then its neighborhood contains nodes 2 and 4. And here in this case, we take the neighborhood this contains nodes 1 and 4. And these are mapped respectively to nodes 2 and 4, so that's the same set. So if you so whether you first take the neighborhood and then map the nodes by the isomorphism, or first map by the isomorphism and then take the neighborhood, that does give you the same set as you would require of a structure preserving isomorphism. Now we can construct some functors on this groupoid of graphs. A simple example is a scalar. So we can assign to a graph just one real number, and we can assign to any graph isomorphism the identity map between the real numbers. Another representation is the vector representation. So we can assign to a graph of 4 nodes a 4-dimensional vector space, and then if we map by a permutation, if we map with a graph isomorphism, then we apply the isomorphism also on the set of dimensions of the vector, and then we transform this vector as such. So in this case, we map, for example, node 1, node 1 to node 2, and that's why we map the first dimension to the second dimension in the vector space. Then we can also construct higher order representations, and these, for example, are matrices. So here we would assign to this 4-dimensional vector space, so for a graph with 4 nodes, the vector space of 4x4 matrices, and we and graph isomorphisms are mapped to linear maps between these matrices by permuting the rows and columns of the matrix. So now we can simply say that a natural graph network, given 2 representations of the graph groupoid, is a natural transformation between the 2 functors. Concretely, this entails that for every graph, we assign it an input and an input vector space rho of G and an output vector space rho prime of G. And we also have a component of the natural transformation that maps from the input vector space to the output vector space. And this needs to satisfy constraints, namely for every automorphism. So for a graph A, for every automorphism of this graph, we get an equivariance constraint on the component alpha A. And whenever we have an isomorphism from a graph A to a graph B, then we get weight sharing between the component alpha A and alpha B. So this is quite different from conventional equivariant graph networks, whereby we only have a single transformation for all graphs. Here we see that in more generality, we can have different neural networks or linear transformations for different graphs, as long as these networks are constrained by the automorphisms and are weight shared between any 2 isomorphic graphs. To give you an example, so if we have, let's map from, let's have a natural transformation from the vector representation to the vector representation. Then if we have this graph, and we have an automorphism between the graph, from this graph to itself by swapping the node 2 and node 4. Now the natural transformations for this, the component of it for this graph, and for example, we can, for simplicity now, only look at maps that map between adjacent nodes. So we leave a couple of the dimensions 0 in the matrix. So this is a map from a 4-dimensional to a 4-dimensional vector space. So it's a 4x4 matrix. And we assign it some colors. And what we require is that whenever we apply an automorphism to the graph, and that for any automorphism of the graph, if we apply it to the left and to the that if we so the equivariance diagram here basically means that first applying the automorphism and then the matrix yields the same as applying the matrix and then the automorphism. In this concrete case, this corresponds to if we permute the second and the fourth row of this matrix, that we get the same as if we permute the second and fourth column of the matrix. Or equivalently, if we swap the second and fourth column and row of the matrix, that the matrix needs to look the same. So here we can see that, and that's why I also colored these similarly. So if we swap these two columns and these two rows, then we have the same matrix. So we see now that the natural transformation for this particular graph can have quite some free parameters, but also has some constraints, and as encoded here by these colors in the matrices. Now, if you have an isomorphism to a different graph, then we require that the matrix is the same up to the basis transformation given by the isomorphism. So here we see again that the automorphisms of the graph give us constraints on the natural transformations. And whenever we have two graphs that are isomorphic, then their components should be the same up to a basis transformation. Now I would like to relate it a bit to permutation equivariance. And we can do that by thinking of the graphs with n nodes as related to permutations of n objects. So if we have these two graphs and we have an isomorphism between them, then we can basically relate this to a permutation, namely the permutation of 4 objects where we swap the first and the second object. So, and this is functorial, meaning that there's a functor from the graphs with n nodes to the permutation group of n objects. But the important difference here is that this graph is mapped to the unique object in the group corresponding to the permutation, the category of the permutation group, and this object is also mapped to that. So in a way, we lose information by mapping from graphs to permutations. We can see that because the permutation equivariant maps from n objects where the representations are just vector representations. So we can see this as we pick a vector space Rn, and any permutation permutes that vector space. Now, if you look at equivariant transformations between that, and this is also called a deep set, then we see that all the equivariant maps between that are of this shape and only have 2 parameters. Permutation equivariance is very constrained because we have a very large group. We need to be we are constrained by every possible permutation, and that makes that we only have 2 parameters. So now we can do 2 things. If we have a natural graph network, as I sketched, then we have a different component for every graph, and then these are constrained by automorphisms and weight shared by isomorphisms. And if you work this out for 4 graphs, you get roughly 50 parameters. And I did a rough counting error, maybe off by a couple. If we have this is in a way the most general thing we could do. But if we do what is often called an equivariant graph network on in the literature for these representations, where we relate all the graphs to permutations and then build a permutation equivariant network, we only have 2 parameters. So here we see that in this case, by making the natural transformation dependent on the graph, we have a much larger expressivity than because we are constrained only by the automorphisms. Whereas if we forget about the graph and create one transformation for all graphs, then we have much more constraints and thus many fewer parameters. So we have much less expressivity. So that is a reason why you may want to encode this kind of graph structure also in the component in the natural transformation. So this is all very nice in theory, but there are some practical shortcomings if you would try to implement something in practice. First of all, it depends on the isomorphisms and the automorphisms of graphs, and this is a very computationally costly problem. And so you may not want to do this in practice. And there's also very little weight sharing because whenever we have in our test data any graph that of which there wasn't a isomorphic graph in our trained data, we just have no information on how to process it. So what we propose in our paper is to not look at global symmetries of graphs, but look at local symmetries. And I'm just going to briefly sketch how we approach that. So to define such a local natural graph network, we first define a groupoid of nodes, and the neighborhood of nodes, where the morphisms are now isomorphisms not of the entire graph, but only of neighborhoods between the nodes. Then we give nodes a representation so that every node has a vector space and isomorphic nodes, and an isomorphism between nodes has a linear transformation between the vector spaces. Similarly, we define a groupoid of edges and their neighborhoods, and then can define two functors from a groupoid of edges to a groupoid of nodes, corresponding to picking the source or target of the edge. And then we can compose these functors, so we can create a functor from edges, picking the source node, and then the representation to get a functor from the edges to the vector spaces. Or we can map from an edge to the target node, and then to the vector spaces, giving us another functor from the edges to vector spaces. And then we say that a natural graph network is a natural transformation between them. So this is a lot of words, and if you're interested, I encourage you to look at our paper. But roughly what it corresponds to is saying that if we have a graph like this, and here I marked a node P and a node Q with an edge between them, and also a node P and a node P prime and a node Q prime. If you now look at these neighborhoods, you might the neighborhood of this edge P to Q, you might recognize that this neighborhood is isomorphic to the neighborhood from P prime to Q prime. So then we assign to the nodes vector spaces, and then have a linear transformation from the vector space at P to the vector space at Q, basically doing the message passing from P to Q. And similarly, we have a linear map transforming the vector space at P prime to the vector space at Q prime. And now, because these are isomorphic edges, we're going to have weight constraints between the message passing along these edges. Additionally, there are automorphisms in this neighborhood. So this gives us constraints on these matrices, on the message passing matrices. So this is roughly sketched our local version of the natural graph network that is constrained by the local symmetries of the problem. Just to bring this home to a method that is probably very familiar to you, namely graph convolutional networks, or message passing networks on graphs. So these are instances of the more complicated thing I sketched above. If we assign to every node just a d-dimensional vector space, assign to every node isomorphism an identity map, and then we can have an unconstrained map between nodes, and we require that these are constant in every edge. This gives us a message passing where the output at a node P is the aggregation of all the edges that end at P, where you apply the message passing map on the neighbor Q. So we apply this function, then do some aggregation of the outputs, and this is the new feature at output P. And if you combine this with nonlinearities, then we get graph convolutional networks. So this is the very kind of trivial case whereby we require all the edges to have the same map, but in more generality, you could in theory allow all edges to have different message passing kernels, as long as isomorphic edges have isomorphic kernels. And whenever an edge has an automorphism or symmetry, this constrains the edges. And I encourage you to look at our paper if you're interested in learning more. But this ends the story. I hope you find it interesting. There's some future directions. So I think I'm kind of working on generalizing this kind of natural message passing to point clouds and manifolds, where you would have groupoids of maybe geodesics on the manifolds. Another question I'm really interested in is applications of categories that are not groupoids to geometric deep learning. We saw one instance of the monoid equivariance in the deep skill spaces, but I'm very curious and hopeful that there are a lot more interesting examples to be found. And I have also some, and another future direction is to kind of understand a bit more formally the relationship between global and local symmetries, which I've briefly touched on today. So thank you very much, and I'm looking forward to your questions.
Thank you, Pim. So, I mean, if you want, you can read the questions, but I can try to, if there's a lot, I can.
Yes, this I can, let's see, one, when the nodes have the same vertices, aren't you doing a Homestead and transferring it going to be a functor and you do your nada on that? Yeah, it's kind of related. Haven't really worked out the details yet, but it is, you can do that. An important difference though is that your nada lemma generally tells you what the natural transformations are to all morphisms in the category. Our graph category, though, we're only interested in naturality relative to the isomorphisms, because message passing itself is not natural relative to all graph morphisms. So it's a bit subtle, but yeah, it's related. Could I summarize what we gain in geometric deep learning by rewriting equivariance constraints in categorical terms? Yes. So at least in the perspective I have on it, and you could work around that, but I tried to sketch that in the slide where I said that an equivariance constraints leads to a lot of if we're equivariant to all permutations, we get a lot of constraints. And in that case, we saw that we only kind of have 2 free parameters for our linear maps, whereas natural transformations had many more parameters. So we are constrained only by the automorphisms of the graph, not by all permutations, and it gives us more expressivity. You could in theory work around that by kind of looking at pairs of input feature spaces and adjacency matrices and be equivariant relative to that. And in a way, you get something that is very equivalent to a natural transformation then.
I had a quick comment there, which is in theoretical terms, like one of the things that we gained here is that most of what you read about the concept of equivariance applies specifically to groups. And as was brought up earlier, not everything is a group. So it sort of turns out the right generalization of group in this context is category. So there's sort of no way of avoiding that if you want to start talking about different kinds of transformations. In particular, now we can talk about monoids, which there are many non-reversible things that we care about.
Thanks. What is the definition of a groupoid on the manifold that you can use in practice? Yeah, if you look at the thesis of Taco Cohen, the PhD thesis, he gives one notion, which is like a groupoid of radial isometries. That would be a groupoid between all points where you, on a manifold, where you define maps between the neighborhoods as I'm not sure I can reproduce this faithfully now. A better example is the path groupoid. So if you have a manifold, you can define a groupoid whose objects are paths, and whose objects are the points of the manifold, and whose morphisms are an equivalence class of paths on the manifold. You need to take the equivalence class because you want to say that going forward and then going backwards is the same as standing still. So you need to take something called a thin equivalence class or a thin homotopy class of paths, but then you get a path, a groupoid of paths on the manifold. And that's, I guess, the most obvious groupoid to define on a manifold. Alberto asked, how can we count the number of parameters of a natural transformation? So I came to the number 50 for groups of n nodes. How did I get there? I wrote down all, it is a bit sketched, but I wrote down all the isomorphic, all the graphs up to isomorphism of 4 nodes. And then you can look at the automorphism group of all these graphs. You can look at the representation, and then you can use and we know that so we have, for each of these isomorphism classes, we have a map. It needs to be constrained by the automorphism group, and then you can use basic representation theory to figure out what the equivariant linear maps are relative to the automorphism group. So not the all permutation, but only the automorphism. And then I came to this number. So it's basically every generator in your automorphism group gives you a linear constraint, which you can in theory solve, or you can apply Schur's lemma to solve it. And that way you can get, for one specific graph, all the natural transformation or all the equivariant maps. And then you basically take the sum of that over all isomorphism classes of graphs. I hope that answers the question. You can also do this in code. So you could try to find all the isomorphisms and automorphisms of a graph and use like numerical linear algebra. You can do like a singular value decomposition to find all the equivariant maps. You could do that also in an algorithm. And there's a question by Max. Can we use the category theory toolkit to learn a functor from graphs to feature vector spaces? Bruno wrote a paper called Learning Functors by Gradient Descent. So maybe he would like to. So this is not exactly the. I mean, it's not this specific example. But well, let me try to make a comment related to graphs. You could do that. You could, for example, analyze all the graph morphisms. Then you could look at try to have a neural network that inputs a graph morphism and outputs like a linear transformation. And then via gradient descent, you could try to have the functoriality constraint satisfied. And something, maybe Bruno, if you want to comment on that.
Yeah. I mean, so this is an interesting question, and if people know about the architecture called cycle GAN, so cycle consistent generative adversarial networks, there's lots of words there, but the idea is simple. You sort of have two points and two, so you can think of it as two objects and two morphisms going back and forth between them. And this is the example of cycle GAN has this horses and zebras that it learns to transform images one and another. And you don't just have a graph, you have sort of a category because you want this these morphisms to be invertible. So you can think of this as a category, and then you want to have that structure and embed it in some vector spaces where you want to learn a particular transformation that satisfies this isomorphism, and you do that with a functor. So that's sort of the idea, as much as it can be explained with words. So that's, I think the answer is yes. And from what I understand, there's like a lot more work to be done on this front in unpacking the details.
Thanks, Bruno. There's a question. Is an application of adjunctions in geometric deep learning? Yes, at least I know of one. In the context of representation theory, there is an adjunction between induced representations and restricted representations. So it's called Frobenius reciprocity. And it basically says something like, imagine we have a group of translations. Sorry, imagine we have the group of translations and we have a rotation group. To combine these form a special Euclidean group. They have as a subgroup the rotation group. And then there is a relationship between representations on the group of rotations and translations, and the representations of the rotation group. And if you're interested, you can Google Frobenius reciprocity. So that is one instance I know where adjunctions are used in geometric deep learning. I'm kind of trying to understand if one can generalize that to kind of other categories and these natural message passing models I mentioned, but I haven't really figured out the details yet.
I have a question until other people post their own, and mine is more of an open-ended one. So we've seen sort of lots of stuff happening here with graphs and adding structure, imposing it on vector spaces, their representations, and sort of how we can talk about learning over graphs and then adding some constraints. So since a category is a graph that has extra constraints added on it, so my question is maybe twofold. Do you think that like having category inspired neural networks that live over categories, is that an idea you so pursued? And yeah, do you know anything about its outlook?
Yeah, great comment. I mean, in a way, with these local natural message passing, it was a little bit like that in that the vector spaces live over objects in a category, and we, but yeah, it's a very. I'm not really sure. I guess there's a lot of things one can do. I don't really have a good answer to your question. I'm sorry.
Yeah, all right.
There's a question. We've been considering signals where the domain is non-Euclidean that admit some isometry permutation. Can the same be applied to signals that are manifold valued? Yeah, definitely. I mean, I'm currently collaborating on a project where we look at lattice quantum field theories, in which you have like a graph where on each edge you assign a group element of a group like the special unitary group. So you can have a field of group elements, and then you can try to do equivariant methods passing on that. So yeah, this happens. Another example is whereby if you want to do like inference of pose. So a pose can be seen as a translation and a rotation of bringing an object of a canonical pose to how you encounter it in the data. And you can try to infer an element of this group of rotations and translations given the data. So then you would have signals that are also manifold valued. And then you can, if you have some knowledge about equivariance, you can build that into the network. So this exists, yeah. If you're interested, I wrote a paper with collaborators called Explorations in Homeomorphic Autoencoding, where we basically build autoencoders whose output are manifold valued. But there's a lot of other work on that too.
There was a question about algebraic geometry that disappeared. But this is actually something I'm thinking about quite a bit, is some of the extensions of these ideas to in the context of algebraic geometry, because somehow in the context, like Peter and my work, we're thinking about algorithms, and somehow these spaces, they're really not manifolds. So so we've been kind of looking at that, but I don't have anything concrete to point to. I don't know if you do, Pim.
I'm not really qualified to comment on algebraic geometry. No, that's I don't know.
I mean, basically, like you can categorify all the various geometric statements, and then what exactly do you get? And there's a lot to say there.
Interesting.
So Gianfranco, we're like I mean, if you've heard the term tropical scheme, I think like a lot of the things that come up in algorithms are basically tropical schemes, because they are kind of defined in terms of like the min plus semi-ring. So, you know, in particular, there's not some really naive interpretation in terms of manifolds and so on.
All right. Shall we leave it at that?
Sure thing, yeah. Thanks, Pim. This was glad to get to hear about some of these things in more detail.